Welcome to our first webinar of 2025. And I'm also very excited to introduce our co-moderators who will be with us today. There's Caroline Inglis, who, as you know, is our Director of Business Development, and there's Dr. Stephen Mamet. And those two are the ones who are going to be handling the chat. And then when I'm done talking, which will be only about 20-25 minutes at the most, Steve will be handling questions and basically will be moderating that. And for that, I would just want to thank everyone for joining us today. For EMS, this is a big year for us. We are introducing our new sensor and software pack, LIORA, and this is our first webinar outlining some of the things that LIORA can do to help us accelerate site closure. And one of the key things before we start, I just want to acknowledge that how important the land is for where we are. We recognize the importance of responsible environmental stewardship, and that's really why we're all here today. We all want to close as many contaminated sites as possible in an efficient way while reducing environmental liability and protecting our communities and ensuring use of our future generations. And you know, how I view it is everyone here on the call today is carrying on traditions that were started thousands of years ago by our ancestors, wherever they were from, and what we're all doing today on our shared land. And this aligns with EMS's core vision. And our core mission at EMS is to restore, repair, and improve the world's soils. And one of the key things I'm going to highlight today is a concept about the roadmap to closure. And we've all said that, and we wonder about what that means. And sort of, this is my idea of it. This is not specific for any specific regulatory process. My experience is working with regulators around the world is, in essence, they all kind of have the same idea about what is responsible. And I think we would agree with most of those ideas. We might disagree with some of the fine details, but today we're going to take basically a 100,000 foot level overview of that process and what each step is. And the overview of this is that really the roadmap to closure has three distinct components. The first is reducing impact. So this happens post-discovery. So at this stage, you really are trying to reduce your impacts and understand what they're going to mean. And then after you've done that, you're going to be searching for regulatory compliance. And in one way here, what you're doing is you are ensuring that the risk is minimal and that it is going to continue to reduce in the future. And then the final is a closure process. And this closure process is largely that you as a site owner or consultant acting on behalf of your site owner are working with the regulatory bodies so that we can all agree as different stakeholders that this land is now suitable for X purposes. Sometimes that's for sale. Sometimes it's basically continuing to operate on what it is or operate in the future with certain restrictions. And if we just blow up this very first step, which is reducing impacts. So how I think about it is whenever after you've had discovery and assessment, there's really two key things you're interested in. What is the concentration extent of groundwater impacts? And what is the concentration extent of soil impacts? And normally what we'll do is we'll either do intrusive investigations or in our suggestion, we would suggest installing something like a LIORA sensor. And what that starts to do is it starts to be able to tell you if your soil concentrations are going up, going down, same with water. It also allows you to delineate the site. Of course, this will be mixed in with decisions to remediate. And if you've installed something like a LIORA sensor, you can actually evaluate over time, relatively rapidly, what the influence of your intrusive remediation might be. And that remediation can be everything from excavation, could be in situ chemical oxidation, it could be, well, maybe a pump and treat, unlikely, maybe thermal, or could be bioaugmentation or biostimulation. And then the next year you check again and you say, okay, what is the extent of the soil impacts and where's my groundwater? And of course, from my point of view is once you need to first know what's going on with your groundwater. Is it stable? Is it hopefully shrinking? And is there any sort of off-site risk? And then you can also be thinking about what's going to happen with the soil impacts. And if you've installed the sensors and you've been running them for, let's say, 6 months or a year, you're going to have an idea, is the data stable and convincing? Am I seeing consistent decreases or at the very least consistent delineation? And then you move to the next stage. And I call this regulatory compliance. And in essence, there's always three key things. The first is there a low vapor intrusion risk? For most of our hydrocarbon sites, because that's largely what we're talking about here in this particular webinar, really what we're concerned about is vapor intrusion risk on buildings that are present on the site. And we have to confirm that there is very low vapor intrusion risk. The next thing we have to be thinking about is, what is the groundwater plume? Is it stable and ideally shrinking, or at the very least stable? How far is it going to go? And then the final one is high NSAD. And the reason that high NSAD, people think about natural source zone depletion, and that's what NSAD is the acronym for, as a closure process. And it can be, but how I think about it is, remember that 95% of your hydrocarbons are present in the soil. And natural source zone depletion allows you to estimate what's happening to that 95% hidden mass that you do not see. And if that's decreasing and your groundwater is decreasing and you have low vapor risk, then you have a reasonable reason to go forward and engage with the other stakeholders, do the closure process. And so if you can demonstrate sustained risk reduction over a year, maybe 2 years, because remember, our LIORA sensors gather about 17,000 estimates per year. So if you have a reasonable number, let's say 10 sensors on your site, you have 150,000 data points a year, which hopefully will show sustained risk reduction. And if so, then I would suggest you should start moving to some sort of risk-based closure process, whatever happens in your jurisdiction. They're all a little bit different. They all have different requirements. And if not, I'm going to suggest you, if you're pretty convinced that you're going to not need to do additional work, then just monitor for a year and make sure that your intuition and your conceptual site model are in alignment with what the data is actually presenting to you. You think about this as an overview. There's really these 3 steps: reducing impacts, regulatory compliance measures, and then the closure process. And one of the key things we want to highlight today, and one of the big topics of discussion today, is we're going to talk about that, first off, the time difference. And that if you have a well-behaved site, and I can't hear most of you, but I know that most of you are probably thinking, whoever has a well-behaved site, it's like a well-behaved toddler. If you have a well-behaved site, you should be able to get between 1.5 to 2 years to enter the closure process. Whereas with traditional intrusive investigations, you're normally looking at 8 to 12 years. And one of the things, this can be very demoralizing, be very frustrating, but also can end up being very expensive. I'm going to give you an example of a theoretical site. So here's a theoretical site. This is based off my experience working with various sites in which you've had an underground storage tank that's leaked. Pretty common. You get a discovery process happening in the mid 90s. You do a good phase 2 environmental service, an ESA. And then after that, you'll do delineation. You're going to monitor for a couple of years. You're going to do another phase 2 because now you're worried it's not delineated. Do more groundwater monitoring. And then you realize, oh, we're going to have to remove this source. So you do the UST removal. Then you're going to have to do more phase 2s. And at the end of it, you've spent 20 years. You've spent about $750,000, and you really haven't moved the site forward very much. And part of this is the data you're collecting there is heavily non-normal. It's very sparse. And so it's tough to make decisions that you're confident in. And in contrast, when you think about a LIORA sensor, so you start off with the discovery, and let's imagine for this site, you began in 2022, you have a phase 2, you're pretty comfortable with it, there's still some niggles, you start with LIORA monitoring. Well, after 1 year, you have 150,000 data points, and you realize, oh, we're going to have to remove this UST. And so you remove the UST. And you're going to start to develop an LNAMPL management plan because now your sensors are clearly indicating you've successfully removed the UST. You're now going to move forward into long-term management. And notice that this happened in 3 years for about a third of the cost of the traditional approach. And for today, what we're going to talk about in this webinar is how we can do that and how it comes about. So we're going to discuss a typical roadmap to closure. And we're going to outline approaches how you can accelerate progress along the roadmap. Now, when I say a typical roadmap to closure, I mean, we all know that there's often uncertainties or things that happen. We don't know what we don't know on our sites, and that can result in some sites taking a long time to close. And we often focus a lot on that. But what I would ask people to think about and reflect on is how many sites are they working on that they think they could push to closure because it's a pretty routine site, but they just don't have enough data and they worry about cost and time and effort required to close that fairly routine site. And what we're going to talk about today is how the LIORA packages can help you with that. So let's go over a traditional pathway to closure. So on the left, we're going left to right this time. And on the left side, you can see you have a contamination exceedance. And then on the top, That's where you talk about soil, my passion, where you'll assess soil concentrations, determine plume persistence, and then see maybe, hey, is this a site that NSAID is actually happening? In other words, our natural processes actually happen to be at this site, because that informs what sort of remediation I should probably do. On the bottom, we're assessing groundwater concentrations. And a big part of that, of course, is delineation. And then what we're going to need to do is we're going to need to determine plume stability. Well, you'll see shortly that that typically takes about 16 measurements over 4 years. That's kind of the best in class sort of advice we're seeing right now. And at the end of that, you're going to be able to assess the extent of that ozone and plume delineation. So you're going to have an idea about how much and where it is in the soil and what your plume is doing. And once you have that information, then you can say, okay, how am I going to actually move this site to closure? And of course, what you can do is if it is NSAID, if there's a lot of natural remediation happening, you can calculate NSAID rates. And you're going to have to do it. You're going to probably have to monitor that for about 4 years using traditional methods, because traditional methods, if you've got a good team, they might be collecting 4 or 5 NSAID estimates per year at maybe 20 locations on your site. It'll be expensive, but you'll have an idea what natural remediation is occurring there. And then below in the groundwater, you're going to be tracking hydrocarbon reduction. And that you're going to do it in soil here as well as water. And at that point, you're going to have your water and your soil your water and your soil. You're going to have discussions with the regulators, and very formalistically here we've got acceptance, because of course they're just going to go, "You're brilliant, absolutely, we're going to accept it." Of course, that's not really how it works. People are going to go back and forth on this, but typically what we would expect is 8 to 12 years. Now, I know recently when EPA looks at this, they typically see 19 to 23 years for closure. So this is optimistic, I know. 8 to 12 years is what we do with traditional approaches. And of course, what happens during all of this is you end up with delays. For various reasons, you are organizing complex processes at multiple sites, and there can be delays for reasons that are outside of our control or sometimes within our control. And the costs escalate. And the costs are escalating not only due to inflation over 12 years, but just because what's happening is you end up having to redo work. You can imagine when you go into the acceptance process and you've got a phase 2 from 8 years ago, that the regulators can be saying, well, what do you think is happening now? Now, in contrast, if we think about what a LIORA system can do for you, is we can dramatically accelerate that. And the reason is that when we just think about the groundwater here at the lower left, that you can basically get a strong estimate on plume stability within 3 months. Now, that is not going to be enough to prove to a regulator it's plume stable, but you yourself, there's plenty of data at that point. There's, let's see, if you had like 5 sensors in there, you're going to have approximately, 25,000 groundwater estimates. And so from that, you can have an idea, okay, how do I think my plume's doing? And then what you can do is you'd feed that into our plume futures, which is UGS, which is the United States Geological Survey's ModFlow that's linked to our sensors. And you can say, okay, I've got these predictions, and then I'm going to monitor it for a bit and see if they're actually in line with what we're happening. And then what'll happen is if you put in our LIORA in the soil, you're going to be able to get an NSAID measurement every 30 minutes. You're also going to be getting, very importantly, soil hydrocarbon concentrations. And so the sum total of this is you're accelerating your progress down this pathway to about 1.5 to 2 years. So this is our best case scenario. 1.5 to 2 years by LIORA, 8 to 12 years with traditional. As I mentioned, the evidence on the field is that it's about 19 to 25 years to closure, depending on the type of site and the severity of it. And the other easy thing about LIORA is that with the sensors that are in there, is that you're not organizing multiple intrusive investigations. Realistically, you're going to get good estimates of seasonality. It'll allow you to spend less time trying to organize various trucks and drillers, and more time looking at your data and looking through our dashboards and reports, as well as coming up with ideas, innovative ideas on how to manage your site. And overall, this should lead to accelerated closure. So I've mentioned a few times about how much money for groundwater, time and money required to estimate groundwater plume stability. And this table is reproduced by a paper by Chuck Newell's group in 2016, where they asked this very question. They're like, look, if we're going to be doing a lot of M&A, what is the cost of this? And they recognize that on the left side here, in the very first column, you see how often are you going out to measure groundwater? Everything from weekly to every 2 years. And then how long they have a recommended monitoring duration. And that recommended monitoring duration is actually a function of the number of sampling events. The more sampling events you have, the more the more confident you are in your groundwater plume trends. But that is a little complicated because, of course, you need to drag it out a little bit over a couple of years. You wouldn't want to just measure groundwater one day every 5 seconds and then say, I know what's going on. So what they found when they did that is that, in their opinion, ranging from, if you were to go out in person every week for 18 months, it would cost you millions of dollars to do that. You'd get 83 sampling events and you'd be pretty confident in your plume stability estimations. Whereas if you did it every 2 years, yeah, it's only 40K, but it's gonna take you 8 years to actually make that happen. And so here was their recommendation. They said, we think that this is the best spot. You should measure every quarter. About 4 years, going to cost you between $80,000 and $160,000. Now, if we use those same equations for EMS, what we end up calculating is if you measure every 30 minutes, realistically, within that 6 to 9 month window, you're going to end up knowing what your groundwater plume stability is. And that's going to cost you between $20,000 and $40,000. You're getting an enormous number of data points. Now, of course, there's strong seasonality, and some years you're going to see droughts and you're going to see wetter conditions, which will influence the groundwater depending where you are. So I'm not suggesting that you only put these in for 3 months and get groundwater stability. What I'm suggesting is that you, as a site owner consultant, will have a very strong idea on, is this groundwater problem going to be significant or not within 6 months? And then you'll probably want to monitor it for another year and a half before you go to the regulator and say the groundwater is good. And one of the key things I want to highlight to you is when you use the LIORA system, you end up with the ability to really look at, like when we talk about this level of data density, it does allow you to interrogate your site in ways that perhaps you have not been able to do in the past. And so what I have here, I've just brought up that you're taking a look at is you are seeing here our demo dashboard. So this is an example. This is actually where we work. It's not a real site. And on the left side, you have a site map with our 3 different types of sensors. Some are simply water only, some are soil only, and some are combinations. And if you click on one of these soil sensors, you get a pull up here, which gives you your benzene, toluene, ethylbenzene, xylene F1 and F2 in micrograms per kilogram. You get a little call out table here as to what the most recent results are. And then on the right side, you can decide if you want to look at benzene, if that's your critical one, or if you're more interested in, I don't know, F1, where that is. This is, by the way, fake data because data is never this beautiful. And then what you can do is you can take a look at that monthly trend versus a daily trend versus what's been happening over various quarters and various years. And yeah, this data looks fantastic. I wish all our site data looked this great. You can also take a look at things like methane, if you're interested, if people are interested in methane, or for example, if you're interested in what's happening with your oxygen trends. You can then also take a look at, let's say, for example, what's happening at this particular well with your oxygen trend. And that allows you to ask interesting questions about monitored natural attenuation. If you go down here on the right, what you're able to do here is you can take a look at we use the gradient method of NSAD. And so that allows us to calculate at any particular point at, for example, Q4 2022, how much depletion was occurring through the methane pathway, the carbon dioxide pathway, and the oxygen pathway. And for that, we use regulatory standard conversion numbers from either the ITRC or the API document or the SARO document. You can also take a look at that quarterly. You can see what it looks like monthly, as well as daily if you really wanted to. And what's happening here is that you're gonna be able to get a strong estimate. And one of the key things that you can use this for is you can take a look, if you were to track it, let's say over a year or quarters, you can say, oh, well, here's where I installed my remediation system. And remember that natural source zone depletion is really tracking biological activity in soil. And one of the interesting things that EMS, that these LIORA sensors can do is you can go back up here and say, well, what was happening to actually toluene? Was it decreasing when the NSAD went up? And you can make those comparisons directly here, and you can see what's happening in the water and soil at the same time. In addition, what you're able to do at different levels of LIORA package is you can take these water sensors and they feed directly into a mod flow estimate. And what we've done here is that in this mod flow estimate on the left side, what we're taking a look here at the projected mod flow groundwater plume extent and movement over a 20-year period. And you're seeing here in blue, this is the overall groundwater dynamics on the site. And then the different colored isoplines here, these are linked to regulatory guidelines at your particular site. In the middle here, you can take a look at how your area is going to do, as well as how much mass is under various scenarios. We normally look at baseline, don't do anything, and I said D, and then biostimulation. Those are the three defaults we use, but we can adjust to whatever you need. Then the right one is one of the unique aspects of being able to tie modeling to an actual mod flow. So sorry, modeling to our sensor inputs into something called data fusion. And so we're just going to let this GIF reset here in 1 second. You're going to see when it starts out small, starts out a nice, beautiful square, and then it's going to end up as this huge spaghetti. So it starts here. This is what your groundwater model is. This is what your data suggests. And what you're seeing then is the model, as it's getting new sensor data, continues to jump. And every one of these little spaghetti graphs is one model realization. And if I was looking at this, and this was a site I was working on, I would say, well, look, the south and the east is actually pretty well delineated. You have a pretty strong handle there, but you can see there's something going on the west and north side that we're not too sure what's happening. And so I would say this is a great way to identify what you don't know on your site and also plan future work. So for example, if you were looking at this site and you were planning out where your new wells should go into, because you have to replace some water wells, I would certainly say, well, you should probably put something on the west and something on the north to complement what you currently have. Don't really need to do work on the south and the east. And that's the big advantage of the Plume Futures linkage with this sensor data, is it takes this high density data, which really is quite astonishing. I mean, this doesn't really do it justice when you see it like this, because it's smooth. But if we look with this sort of NSND, you can see you are collecting an enormous amount of data. It can be hard, and I'll even tell you myself, when we first invented these sensors, and I teach graduate courses in multivariate statistics, I thought it would be easy to process, and it really is just overwhelming. There's so much data. And so be able to put that into an environmental fate model, update that model over time, and interrogate that model in ways that are useful, that is very, very powerful, in my opinion, for making decisions as we go forward. And I'm going to give you an example here of the sort of decision that you can make when you're doing this. So, for example, let's imagine that you're like, okay, I want to do monitored natural attenuation estimation on my site. So M&A is used for groundwater. So we're interested in trying to understand what are groundwater dynamics. And the key question we're asking is, how far is our plume going to go? Is it actually degrading? So am I expecting my plume to start to shrink over time? And how far is it going to go? And we have sort of we have multiple lines of evidence. But one of the big ones is, what's my electron acceptor use in spatial trends across the plume? And our sensors, LiDAR sensors measure oxygen as one example. They also measure methane. And so at the heart of the plume, you would expect to see no oxygen because it's all been depleted. And then as you move out down here in the tail, you would expect to see the oxygen go up. And that's a strong indication that there's a lot of natural attenuation happening in this plume. And then you can calculate that over time as to how far the plume's going to go. At the same time, if we were to pull out one well, what you want to be able to do is be able to look at decreases over time at that specific well. So here we've got over 18 months, you're seeing this steady decrease. And that gives you a lot of confidence in saying, all right, look, we're really starting to see that leading edge kind of decrease in over time. But we all know that if you just take point in time samples, this is the huge advantage of having these sensors in the ground, is remember, every day they take 48 measurements. 17,000 measurements a year. So if you go out and measure groundwater once a year, or you can take 17,000, or you can partner the two and see how well they align. Because sometimes when you take a point in time sample, it might not align well with what the overall trends are doing just because of what happened at that site today. Now, what made all this possible? Well, what really sets EMS apart is, in essence, an artificial intelligence model that we built back in 2024. And in essence, how it works is we have our calibration system, this is one of our sensor packs that sits in there. We collect raw signal values. We compare that against known gas concentrations. And then we link that in within the bottom here. These are the absorption spectra for our gases of interest: propane, CO2, methane, you name it. We feed it all into there and we create this base model. And then what happens is this base model gets trained up based on the raw signal, known gas concentrations, and that comes into what's called a tuned model. And then down here at the bottom here, this is one of our sensors. And one of these sensors sends this receives this raw data. It goes into, because this little AI model actually lives on this particular sensor. So it takes the raw data and it inverts that model. It says, okay, we got a trained AI model for every single sensor, and it's a little bit different for every sensor. And it's based on known gas concentrations and fundamental physics and our signal values. And then it's going to invert that. And then it's going to calculate all the concentrations: benzene, toluene, ethylbenzene, xylene, F1, F2, methane, and CO2. And then the oxygen sensor, it behaves on its little own lonely. We don't actually use AI for that. So once we do that, it provides you with very unique insights. And one of those insights here, I'll just show you as an example, is this is a graph for those of you who've worked with us before. You know, this is a graph we often include. And what we're trying to do is what we're doing here is we're talking about regional NSAD on the left side. And this is in liters per quarter versus your plume extent. And the idea here is we have an average value. And if you're in the red, we would suggest, hey, you might want to consider a more active remediation approach than what you're doing, or maybe what you're doing now, you should rethink it. And if you're in the green, you're well above average. And it's like, well, you can continue to do that, but from a cost-effective point of view, you can probably move things off of that for a bit, work on a different site, and see how long this site continues to perform. Because maybe when you've set it up now, it's going to start to remediate. So that is what fundamentally sets EMS apart from other companies that are providing services. Now, the other thing that we can do is, because of the way these sensors are, is we can really offer cost-effective gradient methods for NSAD. You know, the gradient method is the most robust currently of the NSAD measurement, so natural source zone depletion. And so what a natural source zone depletion is doing is, when you have LNAPL that's sitting smeared here between the water and the lower vadose zone, or sometimes the upper vadose zone, what happens is that we end up using up all the available electron acceptors. And then what ends up happening is we have fermentation starts occurring, and the fermentation byproducts, which are organic acids, feed into methanogens, and these methanogens produce methane. The methane starts to migrate up because you're basically getting ebullition and you're getting high levels of methane and CO2 being produced. And as that migrates, comes up, it starts to interact with oxygen. And the oxygen feeds a group of organisms called methanotrophs. Methanotrophs eat that methane, and they use oxygen to do that. When they do that, they release a tremendous amount of heat. And that's why a lot of NSAD estimates will also use heat measurements. We don't do that. There are some good companies we recommend if you're interested in the heat method. But this method, this gradient method of gas determination, allows us to estimate what the flux is. In other words, we get a flux estimate of how much methane is being produced. It's called J, how much oxygen, how much CO2, and then we can back convert that into what your natural source zone depletion is. The key thing that LIORA can do that other people cannot do, any other NSAD cannot do this, we can actually measure the changes on this same gradient of hydrocarbons. And so by measuring the hydrocarbon change over time, we can confirm that, hey, these indicators of NSAD, because that's what methane, oxygen, and CO2 are confirming with what we're seeing in the soil vapor phase and the soil concentrations and groundwater concentrations. And so this allows you to use what's been termed sort of the most robust method to estimate NSAD in a very cost-effective manner. That, again, every one of these little gradients provides you 17,000 estimates per day. We can then also link that. I mentioned this very briefly, but what you're able to do is you're able to do scenario planning. So here is an example. We just laid them out in different roads. You can actually take a look at baseline. I'm not going to do anything. NSAD. I'm going to track NSAD and biostim. And so we just use these as placeholders, but you can use this to link to what you want to do, and then you can feed it into the model that has been informed by this data collected from your specific site to understand what's going to happen in the future. And for my mind, that provides you a lot of insights into future behavior at your site. So two of our teams here is myself and Steve. We both have great names. Interesting fun fact, we have the exact same middle name as well, Douglas. The top 1% of experts in the field of environmental science, that's what we tell each other every day. And no one's contradicted us, so we'll continue saying that. What are the key takeaways here? Well, the LiDAR systems and this scenario where you're going to use modeling linked to autonomous sensors and you're causing data fusion through a whole bunch of technical details we don't need to get into right now, really can allow you to accelerate through closure. And it allows you to do that because it provides you with this ability to sort of see ahead of time and be more I don't want to say more proactive, but you can react to what's going on in your site quickly and not end up in a holding game. Typically, using the same sort of process for the site, you would see be 8 to 12 years. It really allows you to become more efficient, operationally efficient, and also we're building these AI-powered insights and automation. And where we think about where we are today, so what I really focused on today is our data streams, this ability to collect, typically on most of our sites, most of our customers collect 150,000 data sets a year. And what that links into tomorrow, which is this plume futures, which is really a mod flow estimate that's linked to our data, and then linking that in the future where, we're going to be linking this information and linking this with soil properties and what we know about the site to come up with suggestions and insights that are going to be tailored to you specifically and your site. And that's where today we're really excited about is sort of really revolutionizing what your toolkit's going to look like over the next year. I'd like to thank you for your time. I'm going to stop presenting at this time and we'll open the floor to questions.